Hello everyone and welcome to this lecture. Today we are going to see more examples of contour integrals, but today we will choose some different contours, and for today we are going to use some polar representations rather than the Cartesian ones, because we will see that our life gets a lot of advantages when we switch to polar parameterization. So let's start with some example. Again, we are going to use some function f of z, and we want to integrate this thing over some contour. But now today we are going to give another sign in this integral, that is a circle, like this. So whenever you see this circle inside of an integral, this means closed contour. That means a contour that closes on itself. That means the starting point and the ending point are the same. So it's like a loop. So if you recall, one of the example of this closed contour is a circle like this. This is a closed contour. And today we are going to see some integrals that will involve this kind of contours. So let's take the first example, that is example 1. We have to integrate z bar dz, same thing as before, but now it is given that we have to integrate this thing over a circle with unit radius or radius 1, and this circle encloses the origin. So this part means that encloses the origin. It means that the circle's center is at the origin. So that's one way to see it, because but encloses is a general idea. This means that whatever that circle is, the origin will be enclosed by the perimeter of the circle. So let's add another constraint, that is the circle has center at the origin. So the first thing we are going to do is that we are going to draw the contour itself on one side. So let's say this is my Argand diagram, and this is some unit radius, and this is our circle. So this is a circle, though it doesn't look like a circle completely, but yeah, this is a circle. And this circle can be parameterized. Since the radius is fixed, it can be parameterized by only one variable, and or let's say one parameter, that is called the angle that it makes with the real axis, positive real axis, and it starts from theta starts from 0 and all the way to 2 pi. And if you recall that this is the same thing as representing a complex number in the polar form, so we can parameterize the path or the contour by z is equals to r e to the power I theta, but r here is just 1 because the circle has a radius 1. So you just have to write e to the power I theta, where theta will go from 0 to 2 pi. Okay, and this is a closed contour. So now what we are going to do, this is our parameterization choice, this guy over here in equation 1. And now you're going to just use this thing, and you're going to evaluate this integral over here. So first put z bar, and then you have to evaluate dz. So let's do the dz thing first. Since z is equals to e to the power I theta, you can easily deduce that dz will be just I e to the power I theta d theta, right? Just like u substitution. that you are familiar from real variable calculus. And z bar will be e to the power I theta whole bar, that is just e to the power minus I theta. So our theta starts from 0. This is the theta minimum, that is the starting point. So this will be the lower limit in the integral, because we are shifting from z to theta. So instead of integrating, thinking of integration as a variable of z, you can now shift this thing into the theta parameter, and the starting point is, since you are enclosing the whole thing, the whole circle, the starting point is just theta is equals to 0, and the stopping point, or let's say the last point that will correspond to theta max, is just 2 pi, since you are closing this whole circle. That is, you're starting from here, you're going all over this place and returning back over here. So let's now write this integral z bar dz as 0 to 2 pi. Z bar means e to the power I theta, sorry, minus I theta, and dz means there will be I and e to the power I theta d theta, right? And this is a very simple integration. It's just I d theta 0 to 2 pi, and this is just 2 pi I. That's it. So a clever choice of this parameterization will help you to evaluate contour integrals pretty easily. Obviously, it will depend on the problem and the contour that you are dealing with. Similarly, what you can do is that now you can consider another example that is also defined on the same contour, that is a circle of denoted by z is equals to e to the power I theta, and this time your closed loop, or let's say the closed contour integral, is given by z square dz. So again recall that z is equals to just e to the power I theta. So similarly, you will have, just like this problem over here, you will have to write 0 to 2 pi. Again, this is a circle. Remember, I can also take a semicircle and the result will change in that case, and I'll show that in a bit. So let me just say theta varies from 0 to 2 pi. This means a full circle. So this is just e to the power 2 I theta. There will be a I over here, and e to the power I theta d theta, and you have e to the power 3 I theta d theta from 0 to 2 pi, and it's I. And if you integrate this thing considering I as a constant, which it is, so there is 1 upon 3i and e to the power 6 pi I minus 1. This is coming from just evaluating this integration, that is putting the value, 3i theta, and there will be a 2 pi over here and 0 over here, so that is just 3i e to the power 6 pi I minus 1, because e to the power 0, because when theta is equals to 0, that will be e to the power 0, and that is just 1. So now you can see that e to the power 6 pi I, right? So how can you simplify this? Just notice this, that e to the power 2 pi I whole cube, and this e to the power 2 pi I is always 1, right? And 1 cube is just 1, so this whole thing is just 1. And you can see there is a 1 over here and 1 over there, so this thing actually cancel each other out. That is e to the power 6 pi I minus 1. This is just 0, so this whole thing is 0. Now let's try to evaluate the same integral, but now from 0 to pi. That is, when you do 0 to pi, that is, you are starting from here, that is the starting point, and pi means this is the stopping point. So this is another only one half of that contour that we chose before. Before we chose the full circle, and now I'm choosing this part, that is the upper portion. So everything will be same, but here the integration limit will get changed. Instead of 0 to 2 pi, it will be from 0 to pi. So if you just do it like this, 0 to pi e to the power 3i theta d theta, you will have I 1 by 3i e to the power 3i theta pi to 0, right? Yeah. So now you just have to put your values in instead of thetas. So this 2i will cancel out. This is just 1 over, 1 by 3, and there you'll have e to the power 3 pi I minus 1. And now if you recall that e to the power I theta is equals to cosine theta plus I sine theta. So now you can evaluate this value of e to the power 3 pi I, and you can see that now the value has got changed because of change on the path, and also the limits, that is the integration limits, they also got changed. So up to this point your answer is acceptable. Also, if you want, you can numerically evaluate this thing. It will contain some real part and some imaginary part. Obviously you can see that this 3 pi, when it goes into the sine part, that is sine 3 pi, we know that sine n pi, when n is an integer, is 0. So this cos is again either plus or minus 1. So if you don't want to use a calculator, you can just draw the cosine curve. This is 1 pi, this is another pi, this is another pi. So sorry, this is a pi by 2. So this is a pi. This is after 1 pi. So 2 pi will be over something somewhere over here. This is 2 pi, and the 3 pi will be over here, that is minus 1. So this thing will be minus 1, and you have minus 2 by 3. Obviously you can always check with calculator, or you can also keep this thing like this, and you can see that here z squared dz is giving me something else, and this is another contour, that is c prime. So yeah, contour integrals are indeed path dependent. Now before we go on, we want to consider a last example for today, and again we are going to use the parameterization over a circle, but this time you are given, for this example, z is equals to 2 e to the power I theta. So this obviously tells you that this is a circle of radius 2 now. However, the theta is now from pi to 2 pi, or if you want to be more mathematically accurate, this is just the bound on theta. So what does this mean? Let's try to draw this thing first and see what does this mean, because you can obviously find the limits for theta over here. This is the lower limit, this is the upper limit, and the graphical representation GR, that is the graphical representation, is that since this is a circle of radius 2, and you can see that it starts from pi and it ends up in 2 pi. So if this is your Argand diagram, the contour is starting from pi. So this is pi, right? And it will go from pi to 2 pi. So it's going anti-clockwise. So this is a positively oriented contour. And you can see this is a semicircle on the lower half plane on the Argand diagram. So now what you want to do, you want to consider an integral f of z dz, and this is not a closed integral, closed contour, so I'm not putting this closed sign over here. So let's call this contour C3, and this f of z is given by z plus 2 divided by z dz over this C3 contour. Now what I'm going to do, I'm just going to use the parameterization that I have, that is z is equals to 2 e to the power I theta, and I'm gonna use these limits. So first let's write down the limits, that is from pi to 2 pi, and I'm going to use this parameterization that we saw just now. Z is equals to 2 e to the power I theta, so dz will be 2 I e to the power I theta d theta. Okay, so let's write this thing instead of z plus 2 divided by z. So you will have 2 e to the power I theta plus 2 divided by 2 e to the power I theta, and then instead of dz you need to write this part. So that is just 2i e to the power I theta d theta, and you can see that these parts cancel each other out. There is a 2 over here, you can factor them out, and finally what you have is pi to 2 pi e to the power I theta d theta plus d theta pi to 2 pi. Now you can easily carry out this integration. If you do that, you will have e to the power I theta here, and if you integrate that, this will be just, oh wait, yes, I missed something, I'm sorry about that. There is an I over here. You see this I, it's not getting cancelled out, so there is an I over here. Yeah. And now if we go back to this integration, it will be 1 upon I e to the power I theta 2 pi to pi, and here you will just have 2 pi minus pi, right? Now you just have to put in the values. There is a 2i over here, 1 upon I e to the power 2 pi I minus e to the power pi I plus pi, because there is a 2 pi and pi is over there, so 2 pi minus pi is just pi. Okay, everything looks fine. Now e to the power 2 pi I, it's always 1, and e to the power pi I, this is minus 1, and you can easily verify it using the Euler's identity. So 2i. Now if you carry out the rest of the calculation, that is just putting these numbers over here, so let's do that. It's 1 upon I, and here you have 1, there is a minus 1 and there is a minus over here, so 1 plus 1, there is a pi. Yeah, and now just multiply by 2i because 2i is outside, so you will have a 2 over here and a I over here, so this I and this I will cancel out, these two and these two will get multiplied, so there will be a 4, and then you will have a 2 pi I. This should be your result for evaluating this z plus 2 divided by z by dz along some contour C3, where the C3 is just this semicircle on the lower half of the plane. So these are some rules of thumbs that you need to adopt when you are evaluating a contour integral. That is, you will be given some parameterization, then what you need to do, you need to put these things back into your function, and you have to check for limits, and finally you need to integrate over this parameter. So this is how you can evaluate contour integrals for functions that doesn't contain any type of singularity, but the functions that does contain singularity and have some improper limit, that is like infinity and all that, those will be a discussion for later, because you will need something called a residue theorem, and without residue theorem it's very tough to do them. So far we have only discussed these simple cases, that is, you have some parameterization and then you put these parameterizations back and then you integrate. So far this is our discussion on contour integrals. So this will be it for today, and I'll see you guys in the next lecture. Thank you.